Okay, so let's talk about finding the derivative of a function that is the inverse of another function. So f of x and g of x are inverses of each other. That's given. I'm giving you a specific point. F of 1 is 7, and here's f of x. Sure enough, when you plug in 1 cubed plus 2 times 1 plus 4, that gives you 7. Okay, so I want to find g prime of 7. So I'm looking for the derivative of the inverse of this function at a specific x value. Pause the video and see if you can try this. Now, this is sneaky. I mean, finding the inverse isn't too bad. Remember, of course, inverses, the x becomes the y and the y's become the x, because whatever a function does, the inverse undoes that. But usually, what we would do now is solve for y, right? And then we'd have a new function and we would take the derivative. But clearly, I can't really easily solve for y. So what are we to do? Any ideas? Sure, we could try implicit differentiation. Let's try that. The derivative of x is 1. Derivative of y cubed, 3y squared. Don't forget your chain rule, times y prime or dy dx. Plus derivative of 2y is 2 times the chain rule, dy dx. Derivative of 4 is 0. I'm going to factor out my dy dx. And I have dy dx equals, so I'll now call it g prime equals 1 divided by 3y squared plus 2. All right, seems like I'm on my way, but I have a little bit of a quandary. I'm looking for the derivative when x is 7, and I found a derivative for g in terms of y. Gosh, what should I do? Stop the video and see if you can come up with a solution. All right, did you see what I saw? Do you see what I see? I see a point of f of x. So when x is 1, I told you that y was 7, right? So doesn't that give us information about g of x? It sure does. If a 1 is turned into a 7 by f of x, that means a 7 is going to be turned into a 1 by its inverse. How cool is that? So when x is 7, g of x is going to be 1. So I can finish this problem by plugging in a 1 for my y. And this gives me 1 over 3 plus 2, or 1/5. How cool. So here we go. If f and g are inverses, then there's something very cool about its composition. If you take the composition of a function with its inverse, whatever you put in, you're going to get it out. Think about this for a moment. If I put in an x, g will turn it into something else, and the f will undo whatever happened, and I'll end up where I began. Remember, an inverse undoes what a function does. Okay, now that we have that, I'm going to ask you to stop the video, and I'm going to ask you to take the derivative of both sides of this equation. Don't forget the chain rule. It's a little weird because it's notation, but you can do it. All right, how did you do? Let's do it together. So here I'm taking the derivative of a function inside of a function. So that's the classic chain rule. So the derivative of the outside, right? There's the derivative of the outside, f prime of g of x, times the derivative of the inside. Oh, that's just the chain rule. Derivative of the outside times the derivative of the inside. Okay, what's the derivative of x? That's 1. Just for fun, I'm going to isolate g prime of x. just going to divide here. And lo and behold, I have something interesting. What I have, my friends, is a roadmap, a way to find the derivative of the inverse of any function. The inverse of a function's derivative is 1 over the original function's derivative evaluated at g of x. Let's go back to this problem, and let's do it with this new theorem in mind. So if I know that g prime of x is 1 over f prime, well, let's see, f prime of x is 3x squared plus 2x. So it's going to be 3g of x squared plus 2g of x. Everybody following that? Again, that's 1 over f prime of g of x. So I took f prime and I replaced the inputs with g of x. All right, so now if I want to find a specific g prime of 7, it's going to be 3 times g of 7 squared plus 2 times g of 7. And I'm kind of back where I was before. So what is g of 7? Oh, g of 7 is 1. So that's going to give me 1 over 3 times 1 squared, which is 3, plus 2 times g of 7, which is 1. And that gives me 1/5, which is what I got doing it the other way.